Hello students, in this video we'll evaluate the Fresnel integrals using contour integration. So the Fresnel integrals are the following. Okay, it's the integral from 0 to infinity of the sine of x squared dx. That's a function we cannot explicitly find an antiderivative in terms of elementary functions, is equal to the integral from 0 to infinity, remarkably, of cosine of x squared dx, and both these values converge to the square root of 2 pi over 4. Okay, beautiful. How do we prove this? We prove this via contour integration. So let's consider the function. We consider f of z is e to the I z squared, like that. In the contour, the following contour. Okay. What's the contour? Here's the imaginary axis. Here's the real axis. And we're going to go along the real axis from 0 up to r. And then we're going to make a circle of radius r up to pi over 4 radians, like this. That's pi over 4, like so. And this is a circle of radius r. So go like this, like so. Excellent. And if we look at that contour over here, and we call this contour over here gamma r, the contour over here gamma r. Okay. And now I know this function f is holomorphic in here, so f is holomorphic. F is holomorphic in gamma r, right, by the interior I mean, and therefore by Cauchy, so by Cauchy, Goursat, what do we have? We have the integral over gamma r f of zeta d zeta is equal to 0, okay? Beautiful. Now, of course, this contour is really 3 curves, right? It's curve number 1 over here, curve number 2 over here, and curve number 3 over here, right? And so this is going to be equal to the integral over 1 of f of zeta d zeta plus the integral over 2 of f of zeta d zeta plus the integral over 3 f of zeta d zeta. And this is valid for any r, right? This is for all r. Of course, here r is greater than 0, okay? So let's do these contours one by one. So of course, the integral over 1 is going to be what? The integral over 1 of f of zeta d zeta is going to be the integral from 0 up to r. And then what? And then I'm going to have e to the I x dx, e to the I x squared dx, which is going to be the integral from 0 to r of e to the what? E to the I, just now we're going to turn into the sines and cosines. So the first one's going to be a cosine of x squared dx plus I, the integral from 0 to r of sine of x squared dx. Beautiful, okay? So that's what the first contribution gives me. Let's look at the second contribution. The second contribution comes from this r, so the integral over 2. Integral over 2. Of f of zeta d zeta is going to be what? Is going to be the integral from 0 up to pi over 4. Then e to the I what? E to the I r, e to the I theta, d theta. And that's a squared, of course, right? Squared d theta. Okay, good. Alrighty, and so now, of course, what does this simplify to? This looks like the integral from 0 to pi over 4. And we're going to watch. We're going to have e to the I, and then we're going to have an r squared, and then we're going to make cosine of theta, cosine of 2 theta rather, cosine of 2 theta, cosine of 2 theta, plus I sine of 2 theta, like so. And then a what? And I have to do a what? And I have to multiply this thing over here by what? The derivative of this, I'm going to have an r I e to the I theta, and like that. Okay, so that's the chain rule. And so then I have an r I e to the I theta d theta, like that. Excellent. Okay, so I claim, of course, that this is going to go to 0 as r goes to infinity, right? So what's going to happen over here? So if I take absolute values everywhere, modulus everywhere, I'm going to have a what? So this I e to the I theta is unimodular, and this I r squared cosine 2 theta is unimodular. And so I'm left with a what? With an e to the negative r. This is going to simplify e to the negative r squared, and then the sine of 2 theta times r, right? So now by Jordan's lemma, this is less than or equal to, by Jordan's inequality, less than or equal to what? A pi over r squared times r, right? And that, of course, pi over r squared times r tends to 0 as r goes to infinity, right? So as r goes to infinity, these terms over here are going to tend to 0. So this contribution of the arc over here tends to 0 as we let r go to infinity. Let's do the final calculation. The final calculation is just going to be the integral over this line segment over here. On 3, f of zeta d zeta does what? Well, I really start where? I really start at, this 3 is parameterized by e to the I pi over 4, and then what? And then I'm just going to move along that's my phase over here, and then I'm just going to have an x, right? X, okay? Where x goes between r and 0, right? So this is going to be the integral from r to 0 of what? Of e to the I, and then x times e to the I pi over 4, e to the I pi over 4, and then times what? Times just e to the I pi over 4, then a dx. And this thing, of course, is squared. But what's this going to simplify to? This is going to be e to the what? This is going to be 1 over root 2, 1 over the square root of 2, integral from r to 0. And I'm going to make this, we'll make this negative, of course. Let's make this negative, and then I'll flip the limits of integration. Okay, so that's going to be negative. Flip the limits of integration now. You're going to go from 0 to r. And I have an e to the what? I have an e to the I. Now, this is going to be pi over 2. That's going to give me an I. This is going to be negative x squared dx. And then the I term over here is going to be an I. So minus I over square root of 2, integral from 0 to r of e to the negative x squared dx, which goes to what as r goes to infinity, right? As r goes to infinity, see these exponentials over here, so recall, if we recall, the integral from 0 to infinity of e to the negative x squared dx is equal to the square root of pi over 2. That's a Gaussian probability integral over here. That gives me, that's basically just equivalent to what the error function gives me. So this approaches what as r goes to infinity? As r goes to infinity, this is going to approach what? This is going to approach the square root of pi over 2 root 2, right? 2 root 2, and then minus I square root of pi over 2 root 2. If I rationalize down by multiplying by root 2, what can we conclude from this thing over here? So we can conclude that as r goes to infinity, this term over here is going to converge to what? This term over here is going to converge to the real part of this thing, which is this expression with a positive sign because they're equal to 0, so I throw it on the other side. So the negative makes me put it to 0. So this plus this is equal to 0. So this cosine term over here gives me what? This, as r goes to infinity, I have the integral from 0 to infinity of cosine of x squared is going to be a root pi over 2 root 2. Is that the same as this? Sure. Multiply the denominator by root 2. I'll have a 4 then, and I'll have a root 2 pi. Similarly, what's going to happen with this sine term over here? That's the imaginary term. The imaginary term over here is going to converge to the exact same value, which is the square root of 2 pi over 4. So these give me the exact values of these Fresnel integrals if I use this particular contour over here and use the Cauchy theorem. Thank you very much.